equations and then solving. The other type of problem we will be solving are completely contrived problems, making the title of this section Applications a bit of a misnomer. Anyhow, although these problems we will be practicing are not the types of problems you will ever use or solve in your real life, they will make you better problem solvers, and the skills will help you solve problems both in class and in your real life. Many different math books offer many different problem-solving strategies. The one that we're going to use from your book is really tailored to the type of problem we're going to be solving. If you solve things by your own strategies, you're not forced to use this by any means. However, this is a very helpful tool as we go along. Step 1. Read the problem and mentally make a list of what is known and what is unknown. Please mentally make a list of what's known and what's unknown, because if you write it down, you're pretty much going to be writing the problem down again. Step 2. Assign a variable to one of the unknown items and write the other unknown items in terms of this. This is a very, very important step in your book. This allows us to have two or more unknowns, all represented by the same letter. If we use different letters, we would need Algebra 2 techniques such as system of equations, which we haven't learned yet. Therefore, this is a very, very important step, and it will be a difficult step to grasp as we go into the harder problems. When you're done with that, we move on to step 3. Step 3 says, reread the problem and write an equation using the items from step 1 and 2. You may need to find an appropriate formula. Step 3 can be the most challenging step of all of these. In step 2, you struggle to represent everything with one variable. In step 3, you have to organize those into an equation. As we move on to doing age problems later in this section, you'll start to see how hard that is. Step 4. Solve the equation found in step 3. I think this should be an easy step by this point. We've spent a lot of time learning how to solve algebraic equations now, so this is all the old stuff just being put to use. Step 5. Write your answer using a complete sentence. This is an important step because word problems should be answered in complete sentences, and it also shows that you understand the problem. For the first type of problem that we have, translating mathematical sentences into equations, we're going to need to understand some of the words that imply certain operations. This will also be helpful when we all interpret real-world problems and try to write equations to represent them. Words for addition: sum, together, and more than, increased by, deposit. There's more words than this, but this is just a sample of words that you could hear in everyday life that are going to tell you that you need to be adding. The one I need you to be very careful about is the word and. 5 and 4 is 9. In that case, it meant addition. However, the difference between 5 and 4 is 1. Their difference implied subtraction was the operation, and was just used to connect the two words. This is something you're going to have to be very careful about as you go through. The word and does not always mean addition. For subtraction, some words that mean subtraction are difference, less than, decreased by, withdrawal. I'm sure you can think of more on your own, but this is sufficient just to get you thinking about it. Multiplication. The fancy word for the answer to a multiplication problem is the product. Other words that can mean multiplication: times, of, I don't have it listed there, but by, a 2 by 4 is really telling you how to find the area of a piece of wood. For division, we have quotient, into, to separate equally. If you understand what the idea of division is, most of the words we would normally use will represent that. However, quotient doesn't really sound like something we would normally use. That's the fancy mathematics word for the answer to a division problem. Then another important one to know is equals. For equals, the word is, and all of the tenses of that, was, will be, those all imply equalities. And the same or resultant would also apply equals. We're going to start off trying to translate a mathematical sentence into an equation and solve it. We'll start off with an easier example. The sum of twice a number and 5 is 11. Find the number. I'd like you to hit pause and try to solve this equation on your own. The number in question here is just referred to as the number. We know we're supposed to find the sum of twice that number and 5, which means we're adding 5 to 2 times the number we don't know. We write this as 2n plus 5 equals 11. To solve this equation, we need to isolate the variable term 2n by using the addition property of equality. The form that takes is subtracting 5 from both sides of the equation. This gives us 2n equals 6. The last step here is to use the multiplication property of equality to get the n completely by itself. Therefore, we divide both sides of the equation by 2, and we're left with n equals 3. The next problem on your screen is a lot more challenging than the last one. Please hit pause and carefully try it on your own. When you're ready, hit play and continue to see how this is solved. What a lot of people do in solving this equation is they ignore that it's 3 times the difference of a number and 2, and instead write 3 times a number minus 2. That's what's shown here, 3x minus 2 minus 6 equals 3. If that was to be spoken verbally, that would be the difference of 3 times a number and 2, as opposed to what the problem says, 3 times the difference of a number and 2. So if you have 3x minus 2 equals 3x minus 2 minus 6 equals 3, you're close, but you don't quite have it. Note, on this side I've included parentheses around the x minus 2. This tells me I'm finding the difference of a number and 2, then multiplying it by 3, which is what the problem asks us to do in the first place. For future reference, a good hint that you need to use parentheses is anytime you have 2 operations in a row without a number in between. Note, in this problem it says 3 times the difference. So we have times the difference without any numbers in between. That was the hint that we needed to use parentheses. That might be something worth writing down if you're going to have a hard time remembering it. It's a very good clue for these difficult problems. Once we have it written correctly as 3 parentheses x minus 2 minus 6 equals 3, then we're going to use FOILing to start to simplify the left side of the equation. This gives us 3x minus 6 minus 6 equals 3. Now we continue to simplify the left side of the equation by combining like terms. Negative 6 minus 6 equals negative 12, leaving us with 3x minus 12 equals 3. Now that both sides of the equation are fully simplified, we use the addition property of equality to isolate the variable term 3x. We do this by adding 12 to both sides. That gives us 3x equals 15. Now we divide both sides of the equation by 3 to get the x by itself. This leaves us with x equals 5. This is the first of our really contrived age problems. These problems can be quite difficult and really frustrating for students. A lot of times it takes students quite a few practice problems before they actually understand this. So I strongly suggest actually going through this slide by slide with me kind of instructing you some helps as opposed to trying it first. There will be a practice problem right afterwards so you can try to apply these skills, but this problem I would follow along. The problem we're looking at is Pete is 5 years older than Mary. 5 years ago, Pete was twice as old as Mary. We want to find their ages now. For this problem, we're going to use the problem-solving blueprint that was outlined. So step 1 we've already taken care of. That was just read the problem. Mentally, let's make a list of what we know. We know Pete's 5 years older than Mary. We know 5 years ago he was twice as old. More importantly right now is what we don't know. We don't know their ages now. Step 2 of our blueprint for problem solving said to assign a variable to one of the unknowns. Note here we have 2 unknowns. We don't know Pete's age and we don't know Mary's age. A personal suggestion I'll make to avoid having to work with fractions or negative numbers is to always make the smaller age or the smaller value the variable. So here we have Pete's 5 years older than Mary, so Mary's younger, thus we're going to make Mary our variable. We're going to call Mary X. However, we can't just call Pete Y then. Step 2 of our problem-solving procedures, it said try to write both of their ages with that same variable. So now that Mary is X, what can we call Pete so that he's still represented with the variable X? If we have to represent Pete's age in terms of Mary's age, and we've already called Mary's age X, Pete's 5 years older than Mary, we're going to call him X plus 5. No matter what value gets plugged in for X, as long as we add 5 to it, we'll always be 5 years older than that. Thus, Pete's age will always be 5 years older than Mary's. Now we have to move on and think about a way to represent their ages 5 years ago. There's nowhere in the problem where it tells us what their ages were 5 years ago, but we currently have representation for their ages now. Assume we're talking about someone who's 30 years old now. If they're 30 now, how old were they 5 years ago? Obviously, the answer is 25. What's important is the process of how you got that. You probably took 30, the current age, and subtracted 5 from it. Now, this works for finding anyone's age 5 years ago. To find someone's age 5 years ago, all you do is take their current age and subtract 5 from it. With that, let's try to fill in the chart where it says Mary under 5 years ago. We fill in x minus 5 for Mary's age 5 years ago. This is because Mary's current age, as far as we know, is x, and to find someone's age 5 years ago, you just take their current age and subtract 5 from it. Now, we got to apply that same logic when trying to find Pete's age 5 years ago. Pete's current age is x plus 5. To find his age 5 years ago, we need to subtract 5 from x plus 5. We get Pete's age 5 years ago was x. Once again, that's his current age, x plus 5, minus 5 to get his age 5 years ago. X plus 5 minus 5 simplifies to just x. At this point, all of our unknowns in this problem are represented by expressions containing the same variable. This completes step 2 for us. It was a very difficult task. It's going to take you a while to get that. I wish I could tell you that the hardest and the worst part of this was over. However, step 3 usually is more challenging for students. Now that we have all of our unknowns represented as expressions, we have to go back, reread the problem, and try to find an equation somewhere in there. Then we're going to take those expressions and use them to write an equation. At this point for step 3, when we have to write the equation, I like to read the problem a lot and kind of reword it, tease out something from the problem as I'm reading it. So I'm going to start with the second sentence here. 5 years ago, Pete was twice as old as Mary. 5 years ago, Pete was twice as old as Mary. That means Pete's age 5 years ago was twice Mary's age 5 years ago. To me, that helps set up the equation. Now, that's an equation right there. Pete's age 5 years ago was twice Mary's age 5 years ago. Was is the past tense of is, therefore that's where the equal sign belongs. We've got an expression for Pete's age 5 years ago. Was means equals, twice means 2 times, and we have an expression for Mary's age 5 years ago. So by taking 5 years ago, Pete was twice as old as Mary, and translating that into a much more exact language, Pete's age 5 years ago was twice Mary's age 5 years ago. I now can take that and craft the equation I need to write. So now we're going to do that. Now we want to substitute the expressions we have written in the chart above for the verbal phrases they represent in the sentence below. So Pete's age 5 years ago, x, was, equals, twice, 2 times Mary's age 5 years ago, which was x minus 5. So that gives us the expression x equals 2 times x minus 5. Now that we have an equation, all we have left to do is solve the equation. It's a much easier process from here on out. The first step in solving this equation is to simplify the right-hand side of it. There we have 2 times x minus 5, and we simplify this by using the distributive property. That leaves us with x equals 2x minus 10. Now that both sides of the equation are simplified as far as possible, we want to get all of our x's on the same side of the equation. This still falls under the addition property of equality step, isolating the variable term. Usually we choose to move the smaller variable, but in this case, moving the x that's already by itself to the other side would defeat the purpose. We want to isolate the variable term. So instead we're going to subtract 2x from both sides. This gives us negative x equals negative 10, which when we divide by negative 1 simplifies to positive x equals positive 10. Note, at this point all we have is x equals 10. If you look at the question says find their ages now. So we're supposed to have 2 answers, and I need to know what those answers are. X equals 10 doesn't tell me whether it's Mary's age or Pete's age. How we figure this out is if x equals 10, then every x in that chart we've made is equal to 10. We're curious about what their ages are now, so we're going to plug in 10 into the column where we have ages now, making Mary 10 years old, and Pete 10 plus 5, which is 15. Now to complete this problem, we want to write it out in a complete sentence and get Mary is 10 years old and Pete is 15.